I think we're ready to. I think we're ready to start.
I don't hear it. Hear me?
Oh. Can't hear me. She's probably just on her way. Yeah, that's what I was. She got it. Okay, great. Thank you. Good evening, everybody. I'm Mike Vera. I'm from the School of Math and Natural Science. I'm in physics, and welcome to the 2024 Rayborn Lecture. Obviously, our first thanks have to go to Grayson and Jane Rayborn for making this entire lecture series possible and for all their years of service to the university. I also believe I saw Provost Nail. There he is. I want to thank you for joining us, and of course, Dean Winstead, who is always with us for these events. Our speaker tonight is Dr. John Colosi. He's made a lot of important contributions in ocean acoustics, and at least the parts that I'm most familiar with are propagation modeling. He's the recipient of both the Medwin Prize and the A.B. Wood Medal from the Acoustical Society of America. He got his bachelor's from University of California in San Diego and his PhD from Santa Cruz, and we had the same advisor for our PhD. He currently holds appointments at both the Naval Postgraduate School as well as UC Santa Cruz, and it's been a couple years now. Can I still call the book new?
No, it's 8 years.
A few years ago, he made a book that represented a really much needed update in our field called Sound Propagation Through the Stochastic Ocean. And his talk tonight, as you can see, is called The Sonic Sea, From Climate Change to National Security, Listening In on Our Blue Planet. Please welcome me in joining Dr. John Colosi.
All right, thanks, Mike. Let me echo Mike's gratitude to the Rayborns for inviting me to give this lecture. I'm really excited to be here. I hope it's entertaining, I hope it's insightful, and I hope you learn a little bit. Let's see, do we want to turn this thing off? Is that echoing? Maybe I'm just hearing myself. I'm really looking forward to sharing some nice sea stories with you and sharing the excitement of this field of working in oceanography and acoustics and contributing to national security issues with our U.S. Navy. So this is a picture of us up at the North Pole on the KV Svalbard. So it was a Norwegian icebreaker. And so again, one of the fun things about working in the ocean is you get to go on ships and go to exotic places. And so this was an exciting part of our Arctic acoustics work. It was done in conjunction with the University of California, San Diego, Peter Worcester and Walter Munk's group that I've had a lifelong interaction with. I'll move on to the next. So I just want to do a quick little bio. Mike talked about the places I went to school, but maybe I'll fill in a little bit of interest in this. I was studying physics at UC San Diego. When I applied to college, I applied to one college, UC San Diego, because it was near one of the best surfing beaches in all of California. So you can see how motivational things that maybe are not quite so scientific occur. Being a surfer and being a physicist was a little bit odd, especially when I was trying to get people to go out with me. An enchanted evening of reading physics books wasn't always a woman's idea of the best thing to do. I was always looking around saying, why is she dating that guy? I know Hamiltonian mechanics way better than he does. And so luckily I met a like-minded math major, my wife Denise, also a student at UC San Diego, and 4 kids later and 33 years of marriage, it's the best thing that ever happened to me. But I was introduced to ocean sciences through working at Scripps, at summer jobs. That led me to UC Santa Cruz. So I had the great fortune of UC Berkeley and the University of Washington deciding that I was going to go to graduate school at UC Santa Cruz. And so having this my only choice, a place to go, it was a very fortunate thing to do because I met my advisor, Stan Flatte. There was a great cohort in his laboratory. There was geophysical fluid dynamicist Jeff Fallis, who was on my committee, Jeff Simmon, a Caltech applied mathematics person, and Tim Duda, a recent PhD from Scripps in oceanography. And another fortunate thing, too, is that Jeff Simmon ended up being the program manager in ocean acoustics at ONR. And so pretty much my proposals were funded every time. My success rate was pretty high. So knowing people there are good aspects to that. And then Stan Flatte, who worked very closely with Walter Munk as part of the Jason group, called up Walter and said, I've got a great student that you should have work in your laboratory. And so I went down to Scripps and worked with Walter and Peter, Matt Jetchu, and Bruce Cornell. Mike, by the way, did the same thing too. So we followed a similar route. And that's where I really learned. I did much more of a computational and theoretical thesis. And that's where I really learned about observational acoustics. And I learned about getting seasick and all the other things that come with that. So a lifelong relationship with that group. And then I ventured off to the Woods Hole Oceanographic Institution, where I had many, many great mentors going into observational oceanography, leadership and teaching. You know, Jim Lynch, Tim Duda, Tim Stanton. So I reconnected with Tim Stanton, Arthur Bagger, George Frisk, and a host of others. And then at the Naval Postgraduate School, I went into a professorial position. Woods Hole is a scientific institution with just researchers, and I learned about university politics and serving the broader acoustics community. Woods Hole had a very unstratified leadership structure. So it was the scientists and then a thin layer of administrators. NPS has every conceivable layer of administration you can imagine, and every single layer is a new place for a turf war. So that was really kind of an eye-opener, going from a real, bottom-up organization to a top-down organization. So that's a little bit where I was at going through my career. And so as a bit of a preamble, so I'm a professor at the Oceanography Department, and we educate Navy METOC officers in both the oceanography and the meteorology curriculum. These are what we call restricted line officers, because they have to get a degree, a master's degree, because they have to forecast both the ocean and the atmosphere. And then we have these unrestricted line officers. They are surface warfare officers, submariners, pilots, and they're in the undersea warfare curriculum. And so we primarily grant MS degrees. There's a few PhDs. And the funnest thing about this job is teaching the Tactical Oceanography course. So it's a capstone course that takes all the stuff that the students have learned in their 2 years at NPS, going all the way from acoustics, physical oceanography, meteorology, signal processing, probability and statistics, modeling and simulation, and operational factors. And we're trying to put this all together so that they can do a better job at advising the Navy about environmental conditions. So the hypothesis is that environmental awareness conveys a significant tactical advantage to a commanding officer. All right, so kind of the outline and theme of this talk. So thinking about national defense systems, they operate globally in terrestrial, space, and oceanic environments. The performance of these systems depends on the environment. So the environment is where we have our expertise, and so we're constantly trying to put that intelligence together. You can think of it as environmental intelligence to make those systems work better. But at the same time, the systems are providing us information about the environment, and that's something we'd like to take advantage of as natural scientists to answer questions maybe about climate change, about where marine mammals are located, what the ice is melting or not. And so there's some really great systems that we can only dream of in our academic and our university environments about having access to these things. So our U.S. Navy is global. It's in every corner of the world, and we can take advantage of that. So one example is there's a system called the SOSA system. It was developed in the 50s and 60s to track Soviet submarines. So they're underwater antennas, acoustic antennas. They were able to triangulate the Russian submarine. and served us very, very well. And this engineering feat was absolutely amazing. They had a huge number of these arrays in the Atlantic. They have a huge number of the arrays in the Pacific. And they really allowed us to stay on top of the Soviet submarines for many, many decades. But what happened after the Cold War, we started thinking about swords to plowshares types of ideas and how we could maybe use the SOSA stations in other ways. And one of the first things that they did was hand the SOSA stations over to biologists, and they were tracking whales up and down the California coast. And you talk to the watchstanders in the SOSA stations, and they say, of course, like all we could hear was the darn whales. I couldn't hear the submarine because there's so many whales out there. So we were able to track whales and understand their migratory routes and how they were going around ocean features and eddies where there's food, and they're avoiding the places where there's no food. Huge amount of information that was gleaned by these extensive arrays that essentially occupied a whole ocean basin. There was also satellite surveillance. We had very sophisticated satellites looking at the Soviet Union military bases and watching what they were doing. And this is actually, both of these things were due to then Vice President Gore, who set up a group called Medea, who was helping to allow access to some of these resources. And so these satellites now that were great at look at very, very fine detail in Soviet laboratories and research areas, suddenly we'll aim them at the rainforest, and we're understanding better how deforestation is occurring. You aim them at glaciers and see how the glaciers are retreating. Just an unprecedented data set that you just could never imagine getting any other way. And then we had submarines doing transects under the Arctic and looking at the ice and measuring the warming of the water. And there was a big acoustic experiment with the Russians we did at that time. And so lots of really great opportunities to kind of pull together, the national security world and the natural science world. So what I'm going to talk about here is the connection between national security and some fundamental ocean physics. So there's a couple of topics from my Tactical Oceanography course. So we'll talk about eddies, that's essentially the weather of the ocean. We'll talk about tides that we're all familiar with. You think that's kind of boring, but there's actually some pretty crazy things that happen with tides. There's internal waves and surface gravity waves. And so a lot of those processes are talked about in my book right there that Mike mentioned. So this was an update of a book that my thesis advisor, Stan Flatte, wrote with Munk and several other people called Sound Propagation Through the Fluctuating Ocean. I just slightly changed the title, but brought it as an update. And I should say, too, to Mike, I had no choice but to write this book, because Stan Flatte's wife, Renelda, constantly called me and emailed me, when are you going to write the book? Because Stan was so adamant about that book coming out, because they really kind of rushed the first book together. It was a bunch of the Jasons. So Jason is a group of academic researchers that meets in La Jolla now every summer, and they work on national security problems for the government. Stan was part of the Jasons, and Walter Munk was part of the Jasons. And the original book kind of came out of many of the Jason summer studies, but this one really was able to kind of pull it all together. So we'll talk about these processes, and then I'll talk about some exciting new research areas in acoustic remote sensing. So small-scale internal wave and turbulence sensing, and some really nice measurements you saw that we've been making up in the Arctic, looking at heat content and how the impact might have on the sea ice. So since a lot of this has to do with acoustics, just a quick little overview of acoustical properties of seawater. So the speed of sound squared is equal to this derivative of the pressure with respect to the density done under adiabatic conditions. And so what this is essentially telling us is about the compressibility of the material. So think about it this way. That derivative is saying if we change the pressure on some parcel of material, what's going to be the resulting change in density once we've applied that pressure adiabatically? And so sound speed comes from this equation, but in principle, because seawater is a very complicated molecular structure, it's really done empirically. And so this equation you can see here is an empirical equation due to a famous guy at the Naval School named Medwin, Hank Medwin. The equations that we use in our real research are much bigger equations. They're involving the temperature, the salinity, and Z is just another name for pressure or depth. And so another interesting thing about this equation up above is that Newton was the first one to look at that equation for sound speed. And it's incredible to think that Newton actually made a mistake, but he did make a mistake. Instead of thinking about the compression happening adiabatically, he thought it was isothermal. And so he calculated a value that was too small by about 40%, and it was well within the uncertainties of the measurements. This is for air, mind you, not for water. And so then it was later pointed out that the adiabatic rule could be applied, and the data and the theory came into perfect alignment. So importantly, just sound speed increases with increases in temperature, salinity, or depth. And so it's much more sensitive to temperature. There are these derivatives I'm showing you there. The sound speed change with a change in temperature by 1 degree is more sensitive at lower temperature than at high temperatures. The salinity effect there is shown by that factor of 1.34 per change in a salinity unit. Salinity doesn't change that much in the ocean. There's some places in the Arctic where there's very big changes in salinity, but by and large there's smaller changes in salinity. So that one's generally not important. And then for constant T and S, we have this constant gradient of sound speed, adiabatic gradient, of about 1.6 meters per second per 100 meters. So as I said, sound speed is most sensitive to temperature, but in the Arctic and a few places around the world, you got to be careful about salinity. So this is some example profiles from the Philippine Sea. So on the left here, you see a temperature profile. There's actually 12 temperature profiles according to different months of the year. This is from a climatological atlas. So this is an average of many, many measurements in the Philippine Sea for the different months. And so you can see a nice thermocline. So it's hot at the surface where the sun is putting energy in, and it's getting colder as you go down. If you go over to the salinity, you see that the salinity can't really make up its mind what it's doing. So there's actually some very interesting oceanography water mass structure that's occurring here. It's really not that important for acoustics at this point, but you can see that oscillating salinity pattern with maxima and minima. But the sound speed profiles that you see on the right are really dominated by the thermocline. So you can see the sound speed decreasing as the temperature decreases in the thermocline. You reach a sound channel axis where the sound speed gradient turns around. So instead of decreasing with depth because of the decreasing temperature, once you reach almost uniform temperature, now the pressure effect kicks in. And so that forms a channel, a duct, so that sound can travel in the ocean over very long distances without touching the boundaries. And so this really enables a lot of the ASW work that was done for very, very long range detection. And by the way, the marine organisms know this too. And so the ocean itself is an acoustic medium in which the organisms are taking very much advantage of the way sound moves in this region. Okay, so that's just some quick examples of sound speed structure. So now into ocean eddies. So this is what I really refer to as ocean weather. So this picture here is a satellite altimetry picture showing red and blue sections. And so those red areas are warm eddies, and the blue areas are cold eddies. So they're little circular circulations that are swirling around, propagating around the world's ocean. In the upper right panel, I'm showing you where some of these eddies get generated. So this is a picture of the Gulf Stream off the east coast of the United States. So wherever there's a strong current, there will be instabilities in the flow, and they'll lead to these instabilities that pinch off eddies. So you can see there's a cold side of the front where the Gulf Stream is, and there's a warm side of the front. And so you see a piece of water from the warm side has pinched off and gone into the cold water to the north. And a cold part of the water, which was on the north, was pinched off and pushed into the south. And so these features then propagate around the world's ocean and are very important in really determining the structure of the sound speed profile and many other important dynamical properties. So these features, which people didn't think existed for a long, long time, are part of the cascade of energy from large to small scales in the ocean. So, energy gets input at planetary scale. The equator is hot, the poles are cold. There's a temperature difference. That temperature difference drives the circulation of the atmosphere and the ocean. Those circulations have instabilities, like we just see there in the Gulf Stream. The instabilities give rise to eddies, which are smaller scale than the global scale. And so you see this progression towards smaller and smaller scale, input at large scale, and then going down to smaller scale. So we'll talk more about that when we get into internal waves and turbulence in the ocean later on in the talk. So a key process there in the energy cascade, they're a key process responsible for the enhanced horizontal diffusion of oceanic properties. So the ocean behaves a lot more diffusively than you would think based on molecular diffusion. Molecular diffusion is extremely slow, but we have these chaotic eddy behaviors that sort of act like a molecular chaos that gives rise to viscosity and diffusion processes. And so they are a key process that diffuses a lot of the different properties around, and when people who are doing ocean modeling have to be very careful to try to parameterize this process correctly so that they get the right circulations in the ocean. Nowadays, ocean models are getting down to the point where they're actually resolving the eddies down to that smaller scale, but that wasn't always the case, and their diffusive properties had to be parameterized. Another key thing is they account for 99% of the ocean's kinetic energy. So this was a huge revelation when it was discovered that the ocean had this active weather pattern. So traditional oceanography was that we're going to go out in the ocean and we're going to do profiles of temperature and salinity and pressure, and we're going to calculate the density. And so the density is going to vary across the world's oceans. So if the density is different here than here, there'll be a pressure gradient. So the pressure gradient will want to push the flow from the high pressure to the low pressure. But you have Coriolis that has other ideas. Coriolis say, no, we're not going to go from high pressure to low pressure. I'm going to turn that flow to the right in the northern hemisphere and to the left in the southern hemisphere. And so that gives rise to the circulation patterns from the different density. And the idea was that these were large-scale patterns, because you could go out there, measure the density profile once, go home and have a brandy, and then go calculate what the currents of the world were going to be. But this was an alarming surprise that the ocean had much more structure than was anticipated. And we'll find out about that also when we talk about some of the other processes. These are also associated with enhanced biological activity, and these strong temperature variations have large impacts on sound propagation. So that's your connection to the national security. So I have, my feeling is that the Navy actually discovered eddies 10 years before the physical oceanographers did. So I'm sure there could be some really lively debate on this topic. But what happened in 1960, the SOSUS system, as I was telling you about, this acoustic receiver arrays, they were sent to look for Russian or Soviet submarines. They found out that the structure of the sound speed profile in the vicinity of the array made a big difference. And so they wanted to see how sensitive their measurements on the array for detection and localization were going to be, depending on if you're looking up to the north, or you're looking to the east or to the south, through different water masses. And so this fellow, Gordon Hamilton, who was at Columbia University, set off these precisely timed and located charges, depth charges off Antigua, and they were measured on the SOSUS stations at Bermuda and Eleuthera. And so he did this for a couple of years. They're 1961 to 1963. So on the left hand of that plot, you can see the velocity, the effective velocity of the signals, and then you can see the time delay. So you can see the time is fluctuating by about 200 milliseconds, or 0.2 seconds. And it turns out these fluctuations are consistent with the active mesoscale field that's in that area. So had they not tried to calibrate the SOSUS system, they wouldn't have had this idea that, wow, the ocean's changing a lot more than we thought it was going to be changing. It's not this static environment. And there were similar efforts that were done in the Pacific, off Oahu, Wake, and Eniwetok. So there, the eddy field is a lot weaker, and they saw much more stable arrival pattern. So a national security problem led to a fundamental discovery in physical oceanography. And let's see if I can make this work here. It wasn't working earlier. Okay. All right, so this animation that you see here is a satellite altimeter measurement of the elevation of the sea surface. It's just like the one I showed you previously with the red and the blue blobs of the eddies. But now you can kind of see the dynamical behavior of the eddy field as we circle around the globe. So you can see there's places where there's a lot of eddies, like around the Gulf Stream right there. They end up showing up wherever the currents are strong. So off the Kuroshio, another strong current, the East Australian current, the Agulhas current system off of Africa, and the Brazil current off of South America. And so we see this active eddy field, and so this is something that we're up against when we're trying to do ASW. You also notice too on that far plot, we're seeing sea level rise. So after 2.5 decades of satellite altimetry, we're actually piecing together the global sea level rise patterns that you see in that line right there. So absolutely an amazing instrument that really fundamentally changed how we're looking at both eddies and the climate. But really to get to eddies, so the impact of eddies on sound propagation is extensively studied because they're very energetic features. And this thing called the bathythermograph was developed in that time to try to make measurements. Whoop. My ears aren't sticky enough here. So this thing called the bathythermograph was developed by Adelphus Spilhaus, who was a geophysicist. There was this device, the earliest device would take a profile of temperature and it would etch the measurement into this smoke glass, and you'd use that profile, you kind of tabulate or digitize it, and you get a profile of temperature, and then you assume something about the salinity, and you get a sound speed profile. And there were all sorts of problems with it, and later we developed these things called XBTs, expendable bathythermographs. They're a little more fancy, but they still had a lot of problems. And so, in spite of these measurement techniques, and the development of complex ocean prediction models, we weren't able to be able to predict the effects of eddies on acoustic propagation. And so that led Munk and Wunsch to think about this, like, I think we got this problem the whole wrong way around. Instead of taking the bathythermograph to tell us what the acoustics should be, let's take the acoustics and tell us what the bathythermograph should be telling us. And they developed this idea of acoustic thermometry, or acoustic tomography. And it was going to use arrays like that one there in the Philippine Sea. It was out in 2010, 2011. And use the acoustic transmissions to look at the eddy fields in that region. And then later on, Munk developed acoustic thermometry to observe basin scale warming and sea level rise. And that's that globe right there. And you can see there's two sources. There's one off of San Francisco, there's one off of Kauai, and if they're transmitting to all those nodes, those are SOSUS stations. So utilizing the SOSUS receivers to form an acoustic tomography network in the North Pacific to look at the changing patterns of warm and cold due to natural things like El Nino, La Nina, decadal oscillation of the North Pacific, but also the pattern of anthropogenic climate change, which had its own structure. So it's trying to separate out these spatial structures in that way. Okay, so eddies are a really fascinating field, but now we go to tides. So we're all familiar with the normal gravitational tide that you get when you go to the beach. You see the high tide and the low tide, usually twice a day. And that's what we call a barotropic tide. And so this picture at the top is showing what's called the M2 tide. It's a little bit longer than 12 hours because the Earth and the Moon are rotating in the same direction. And so, in the time it takes the Earth to go around one cycle in a day, the moon's moved a little bit forward. And so the Earth has to go a little bit more to catch up with the moon. And so that's why this dominant tide called M2 is a little bit more than 12 hours. And so you can see the pattern. Also, this pattern has been mapped out using satellite altimetry and really getting very accurate maps of the basic gravitational tides. But what's interesting, when this type of tide flows over topography, it creates an internal wave at tidal frequency called an internal tide. And this is shown in the plot, the global plot shown below, and we see internal tides radiating from some of the major bathymetric features around the world's oceans. So you can point to Hawaii there in the middle of the Pacific Basin. So Hawaii is a perfect internal wave generator because the tides flow almost perfectly across the bathymetry in that region. There's another really strong internal wave maker in the Luzon Strait that causes all sorts of problems for naval operations in that region. So internal tides are very interesting. So in the South China Sea, it creates internal waves. There's some of the largest waves in the whole wide world, 200-meter waves. So I told you I'm a surfer, and the surfers talk about, oh yeah, in Maui they rode a 100-foot wave, or in Portugal they rode a 100-foot wave. This is 100 meters or 200 meters. These are enormous waves. And so they have a big effect on acoustic propagation. They actually have a big effect on submarine navigation because these waves are very rapid changes. They take the thermocline, push it down 200 meters, and bring it up in about 10 to 20 minutes. So if you're trying to keep your buoyancy control on a submarine and you have this big feature come through, it's a big deal. And in fact, there's several stories of Chinese submarines getting in trouble, and you probably don't hear about the cases where they lost the submarine, but we heard a few cases where the captain was a hero and they were able to rescue the submarine after getting pushed down by one of these waves. So they're very, very interesting. The internal tide is also part of this question called tidal dissipation, and I'll talk about that on the next slide. But because the tides are dissipating, it's ending up transferring angular momentum from the rotation of the Earth to the orbit of the moon. And you'll see that really clearly when we go to the next slide. Okay, so two topics here on this slide. So to the left, we can see the South China Sea. This is a SAR radar image of some of these internal waves that are coming from the Luzon Strait, which is on the right of the screen. So you see one front here where it says incident Luzon waves, and then you see another front, it says refracted waves and Dongsha Islands there. So those two groups of waves are 12.4 hours apart. So they're generated at the Luzon Strait every 12.5 hours, and they generate these very abrupt wave features. And down below is a thermistor record, not for these particular waves. This is up on the shelf. And you can see that around 12 noon on May the 9th, this huge surge of warm water getting pushed down over 100 meters as that wave moves up onto the shelf. So very significant features that are extremely important for acoustic propagation in this environment and for submarine navigation. So the other really interesting problem for this is the tidal dissipation problem. So what happens, we know very precisely from astronomical observations that the global tidal dissipation is about 2.5 terawatts. And most of it is due to the oceans. There's a little bit of dissipation due to earth tides, but most of it is due to the ocean. And so as a consequence of this, there's a lengthening of the day and an increase in the Earth-Moon distance. And so this little cartoon due to Kelvin kind of tells you how this is occurring. So the top picture, you can see the tidal bulge is right underneath the moon. So you can see the Earth rotating around, the moon rotating around that, and the tidal bulge right under the moon. That would be the case if there was no dissipation. But if there's some dissipation, then the bulge can either lag or lead the moon. And so in the lower panel, you see that the tidal bulge is ahead of the moon. So the gravitational interaction between, very tiny gravitational interaction between that tidal bulge and the moon is going to provide a torque, and it's going to oppose the rotation of the Earth. So that little torque is going to oppose the rotation, and you're going to see, in that case, you'd have a transfer of the angular momentum from the rotation of the Earth to a wider or to a larger orbit of the Moon. So remember, this is an integral over the whole Earth. So some places the tidal bulge leads, some by it lags, but on average, it's ahead. And so this, we think, has been going on for a very long time. And since we just had an eclipse, there's also some very interesting history of ancient eclipses. You know, an eclipse is a very precise statement about the position of the Earth's rotation and the Moon with respect to the Sun. And so there's ancient accounts of total eclipses being seen to move slowly east. So if you saw an eclipse, say like in Alexandria, you see totality in Alexandria, and then they report it going east, 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 and then it was found in Babylon and then going into Asia. And so it appears that, you know, these accounts kind of reconcile that this might have been going on for quite a while, this type of evolution of the Earth-Moon system. So who would have thought celestial consequences of the Earth-Moon system and a pretty important naval security problem. Okay, so internal waves. So we talked about internal tides and South China Sea waves, but there also exists this random field of waves in the ocean that just pervade the ocean. You can't put a thermometer anywhere in the ocean without measuring this din of random fluctuations in temperature. And these variations are due by and large to internal waves. So internal waves are like surface waves. They exist because there's a density difference. So surface waves exist because there's a density difference between the air and the water. So if you lift the sea surface up, it's surrounded by less dense air, so it's going to be heavy, and it's going to sink, and it's going to overshoot, and then when it's gone past its overshooting place, you have the air surrounded by water, and so that's light, so it's going to buoy up, and so it's going to oscillate. And the same thing happens in the ocean, except for instead of being an interface, it's a continuously changing density profile. So the ocean is stably stratified. There's less dense water, mostly sitting on top of higher density water, and that gets set in motion primarily by winds and by tides. So internal waves were kind of interesting. They were first described by Vikings as dead water. So the Viking warships used to cruise around the fjords, and fjords are famous for having a thin layer of fresh water on the top. So the glacial melt that's in the fjord makes this thin layer, and if you're trying to row a boat with a thin layer over a thick, dense layer, you're going to start generating interface waves on that section. And so instead of your oar power going into you accelerating, your oar power is going into generating these waves, and it feels like something's pulling you. And the Vikings described them as like these sea creatures that are coming in and slowing their boats down, but it was really just internal waves. So as I said, main sources are wind and flow over topography. They're also a pathway for the transfer of energy from large to small scales. So you take eddies, they break up, cause internal waves, and then that energy goes down into mixing and turbulence. They have this link between the large 2D motions of eddies to the 3D motions of turbulence and internal waves. The breaking of these waves have implications for density changes and the shape of the stratification of the ocean. There's also civil engineering impacts that I'll talk about. So we talked about tidal dissipation, Earth-Moon system. Internal waves are also interesting because they radiate momentum instead of diffusing momentum. So remember I talked about the eddies. The eddies lead to this enhanced diffusion of the ocean. And so that diffusion is treated kind of like Fick's law as a random chaotic motion. But internal waves are taking energy and they're radiating them around. That's completely different than diffusion. And so when there's sources and sinks of internal waves, that leads to a body force on the ocean circulation. Is very important for calculating flows properly in ocean models. So because of the importance of internal waves, there's lots of important aspects of acoustics with internal waves. And it all is really due to Garrett and Munk, who put us on the right page with what internal waves were doing in the ocean. And it was really a triumph of tactical oceanography, because ever since the end of World War II, we knew that there were fluctuations in acoustic transmission in the ocean. We just didn't know what was causing it. And so there's this quote here from Carl Eckardt at the bottom of to the right page here. He says, if sound of constant intensity and frequency is transmitted through the sea from one ship and received on another at some fixed distance, the intensity of the received signal will vary from 1 second to the next and not be constant. It fluctuates, often by a factor of 10. Indeed, the presence of fluctuation is perhaps the most constant characteristic of sound in the sea. This is 1950. So this is the Committee on Undersea Warfare, got all the university luminaries together, Eckert at UC San Diego, Carhart at Caltech, and they worked on these national security problems, and they identified these important factors of sound propagation in the ocean. And so from 1950 to 1970, people used ad hoc models for the ocean, trying to predict what fluctuations would be. Munk and Garrett put together a model of the internal wave field, a statistical model, and they applied it to an acoustic propagation theory, and now they're within a factor of 2 of the measurements. Yeah, so it really goes to show that knowing the ocean makes a difference. So environmental intelligence is a force multiplier. So this is an example of some internal waves that we measured in the Philippine Sea. So kind of so there are these black things are the isopycnals. So the isopycnals get pushed up and down by the internal waves. So kind of the slow changes of the eddies, you can see some tidal scale things, and the random component is also evident there. So one of the things that Munk and Garrett did that was so amazing is that they found universally that if you had 2 thermometers separated by 100 meters in the ocean, the fluctuations in temperature from those thermometers would often be uncorrelated. And people just did not believe that the ocean could have that much variability at that small scale. And for almost a decade, they believed there was something wrong with the instruments, that the instruments were doing something incorrectly. But at the end of the day, everything kind of added up together, and then Munk's model really ended up working. So here's some examples of internal waves in coastal regions. So these waves crash into the seashore. They lead to what we call an internal surf zone. And this is some measurements we made off of Vandenberg Air Force Base on the shelf there. So the upper panel is showing the 50-meter isopath, and these are the waves going into the 20-meter isopath. And so you can see that every 12.5-hour surge, that's the big surge of warm water being pushed down. And then there are also these more sharp, abrupt variations that are like the ones we saw in the South China Sea. So they evolve from the internal tide into these sharp features. So it was kind of, when I mentioned civil engineering aspects of internal waves, this leads to kind of a fun story about Huntington Beach. So Huntington Beach is Surf City, USA, but unfortunately their beaches kept getting closed because of polluted water, like high bacterial counts. Well, it turned out, the city of Los Angeles had a sewer pipe that was going out off of Huntington Beach. And what the civil engineers thought they would do is they'd put the outflow of the sewage system right below a big change in the density, what we call the picnic line. So where it goes from very dense water to very light water, so it was kind of capped. But unfortunately, you have these waves rolling along that interface, and the waves picked up the sewage and transported it back on shore. And so they determined that was the reason why the water quality was so bad, and they had to redesign the system to go to further out so that the water quality stayed good. Okay, surface waves are obviously a very important part of tactical oceanography. They're an important part of how the atmosphere drives the ocean. They lead to air-sea interaction processes that are very important. They go into coastlines and redistribute properties. Surface wave breaking, a major source of mid-frequency ambient noise. They carry bubbles into the upper layer of the ocean, which have a big effect on sound. Again, they're a key process that randomizes acoustic signals when you're in regions where the sound is close to that area, and then they impact ASW systems like sonobuoys. These are air-deployed listening devices that if they're getting washed over by waves, you can't hear what they're doing. And just a fun story with Munk. After World War II, Munk worked on predicting the waves for the various amphibious landings, including Normandy. And so they used very, very spotty data on the North Atlantic to try to predict those wave conditions. And in fact, the invasion was delayed one day because the waves were looking to be a little bit better the next day than the day that was planned. But then they also had to be under a new moon where there wasn't any light. So they worked really hard on that problem. And so Munk really wanted to understand, well, how are waves acting globally? Are waves just a local phenomenon, or do you see global propagation of waves? And so Munk developed this thing called flip. So you can see flip, after it's been flipped, like 75% of it is below the surface, and it allowed a very stable platform to observe surface gravity waves. And they did an experiment looking at waves generated off of Antarctica going up all the way to the Gulf of Alaska. And the measurements that you're seeing there are from some of the different stations, starting down at Tutuila, Palmyra, Honolulu, and then at Yakutak. And so you can see we have long period waves come in first. The long waves are fast. The short period waves are slow. And you see the swell spreading out as you go. So when you're close to the source, the swell lasts 3 days. Once you get up to Alaska, you have a 6-day duration. And there's also some really interesting stories about Munk looking at waves generated by nuclear tests, but I don't think I quite have time to get into that. And this is an interesting way in which waves, about surface gravity waves, are interacting with eddies. But I think I'm going to skip along to some of the remote sensing things that I'd like to talk about before it gets too late here. So we're going to talk about ocean mixing and turbulence, Arctic heat flux and heat contact, and ice dynamics. So mixing and turbulence, as I was saying, mixing leads to changes in density and other water properties. And many fundamental ocean and climatological processes are influenced by mixing, since the density impacts the flow. So mixing is difficult to observe because it's intermittent and there's variation over many space and time scales. We have profilers that can kind of measure mixing, but you can just kind of send them every once in a while. They take a long time to probe the whole water column. There's a few moored instruments, but those are kind of being developed now. So what we're thinking about is using acoustic propagation through a turbulent boundary layer to try to understand what the properties of that boundary layer are. And so that turbulent boundary layer is going to lead to scintillation. The scintillation is going to be a marker for the turbulence, and that's going to be our measurement. So Munk just keeps showing up in everything that kind of goes on in oceanography. So Munk had this idea of the thermocline. So when you observe temperature profiles in the ocean, they're nice and smooth. And the reason he thought they were smooth is because there was a competition between downward diffusion due to mixing and upward advection due to deep water formation at high latitudes. So a lot of the deep waters of the world's ocean are created off of Antarctica, and so where there's ice formation and brine rejection, and a lot of heat gets taken out of the water, so it gets very dense. It sinks all the way to the bottom. And so if you didn't have mixing, you'd have this very hot upper layer, and then you'd have this interface with a very cold lower layer. But we don't see that. We see this nice, smooth thermocline. And so if you use this very simple model of competition between diffusion and advection, you find that you get an exponential temperature profile, and the exponential scale factor has to do with the vertical velocity of the advection and the diffusion scale. But what we found is that Antarctic bottom water that we know is rising up into the upper layers it's not rising in the way that Munk said. So if we look at mixing and diffusivity over the ocean, that's the upper right panel, you see that it's highly intensified towards the bottom boundary layer. So there's rough surface effects that are causing instabilities, generating mixing along the bottom boundary layer. And so our acoustics would be a way of monitoring that mixing. And so here we can see there's an intimate connection too between internal waves and mixing. So this is measurements done at Rockall Trough. So the upper panel there is showing temperature surges. Those are tidal surges of internal waves. And then the lower panel is showing you mixing. The mixing is following each tidal surge. So as the internal wave is flowing over the topography, it's sort of spilling over like a surf zone and causing mixing as it goes through. And so one way we can the idea is to use scintillation to look at this process. And so this is just a simulation. This is actually atmospheric laser propagation, but it really shows the scales really nicely. So what I'm looking at is a plane wave propagating through a turbulent medium. And so that plane wave is going to start with a value of 1. It has an amplitude of 1, so that's what this blue is. And as it goes through, it's going to be distorted by the turbulent medium, and you're going to see a pattern developed. And so the pattern that develops is kind of like, shows some small values of this thing called the scintillation index. So that's kind of telling you, it's kind of what the word says. It's how much scintillation you get, how much twinkling of the signal do you get. And so so we'll find that values less than 1 are kind of weak scintillation. We end up going this regime where there's very strong scintillation and caustics formed, and then we kind of go into a scintillation index asymptoting to 1 for what's called saturation. Okay, so this is just kind of in the beginning of the evolution of this wave going through. So you can see there's regions that have been kind of focused up a little bit. The scintillation index is 0.26, and there's regions where you kind of get defocusing. And so that pattern is telling you something about the pattern of the turbulence, in this case, the light going through it. It also kind of looks like the pattern of the bottom of a swimming pool, right? When you get waves and the light comes through the swimming pool, you see the bright and dark bands. So those are going to be caustics we're going to see further. So as you go further out in range, let's see if this allows me to do it. So now you get into much higher scintillation, and so you can see these caustic networks forming and kind of breaking up, so you can see interference fringes around the caustic formations, so very high scintillation. And then as you go to longer range, now you go into a full randomization of the signal. So this is this speckle signal. So there's very little information about the environment in this regime. In the weak fluctuation regime, that's where your most sensitivity is to the environment. And that's what we want to do when we try to make measurements of a boundary layer. So this is a little bit of a busy slide here, but just look to the left here. So we're thinking about having a transmission about 4 kilometers long. So we have a source about 100 meters off of the slope. It's transmitting to a vertical array. And so we're going to measure a direct path that's going through the bottom boundary layer it's indicated by that bracket. So the bottom boundary layer is a couple hundred meters thick. And so we're going to look at the scintillation along that direct path, and we want to be able to separate it from the bottom bounce. So we don't want the bottom bounce getting involved. So this involves getting some pretty high bandwidth sources, and then we need a pretty dense receiver. And then on the right is showing spectra of the scintillation pattern. So a spectrum here is in terms of a vertical wave number. So it's essentially telling you the scale of the fluctuations in the scintillation pattern. So large value along the x-axis means a small wavelength, so small scale scintillation, and then a smaller number means larger wavelength variation. And I have plots there for both. The red plot is showing internal waves, the blue plot is showing turbulence, and the big question is how do those two plots meld together in a boundary layer? We also want to measure both kinetic energy distribution and thermal dissipation. So you have the velocity structure of the turbulence, which is causing the sound to be scattered, but then you also have temperature variations when you have a stratified fluid. And so we're kind of working on observability regimes in this particular setting. So it turns out you want to have enough scintillation that you can measure the turbulence and the internal waves, but not too much that the theory is invalid. And so these are kind of charting out little areas based on different frequencies where you might be able to make that measurement. So my last topic is the Arctic. I'll try to go through this too quickly because I see we're close to our time here. So the Arctic is a sea in transition. It's a no shocker to any oceanographic institution that you go and say this. There's reduction in the extent and thickness of ice cover. Multi-year ice is disappearing. There's smaller ice keels. Warming and freshening of surface and intermediate layers is occurring. The eddy field and internal wave field energies are increasing. And acoustic propagation measurements are sensitive to all of those things. So it's because we don't have satellites to look at the Arctic as well as we like, this is one way of being able to get these in situ measurements. And from the Navy standpoint, what we learned about Arctic propagation during the Cold War is completely obsolete. The stratification is different, the ice is different, everything is totally different. We have to start from scratch. And so with Scripps, Institution of Oceanography, Munk and Worcester and Jetshu's group, they put out this tomography array. It looks just like the one I showed you in the Philippine Sea, except for it's in the Beaufort Sea. And we're looking at a very interesting structure that exists now in the Beaufort Sea. So you see the color picture over there. There's that warm layer right above the blue Pacific winter water. So that warm layer and the warm layer below it forms an acoustic duct, a subsurface acoustic duct. And so you can have sound trapped in that duct that can propagate very far without touching the interfaces. So back in the Cold War, the only way you could get long-range propagation was if you had extremely low frequency. Now, with this subsurface duct, you can get extremely long-range propagation. Well, I've seen 900 hertz detected out of 1,000 kilometers. It's a very stable duct and very interesting tactically for when we start, well, we're already getting pretty active up there. But the question I wanted to ask is, how much of this warm Pacific layer, how much is it warming? We know we've seen it warm over the last several decades, but can we measure that persistently? Because an acoustic measurement is integral. It's giving us an average over a geographical area, and it gives us very important information about that warming. And so if it is warming, can some of the heat get transferred to the ice cover? So if it's getting transferred to the ice cover, then we're going to see greater ice loss. And then can we monitor this acoustically? All right, and so what we use is a normal mode approach. So here's the sound speed profile here. So there's certain modes that are trapped in the surface duct. So this is 250 hertz. So that's the first plot there. This is another acoustic mode that's trapped in the Beaufort duct, and then we have mixed modes. And if we look at our data, this area I say Beaufort duct 1, that's that first mode that's trapped in the Beaufort duct. And then the final cutoff is due to that very last mode that's a mixed mode between the Beaufort duct and the surface layer. And so we can look at these two features, the arrival of that Beaufort duct 1, the first arrival, and the last arrival, and track that in time. And that's what this dot plot is here. So here we're kind of seeing, so the color plot is showing the black dots tracking the first arrival, the white dots tracking the last arrival. We have some problems that the mooring got blown over by the currents. That's what this plot here is showing. We also have some problems that once the ice starts forming, there's a lot of loss. So that last cutoff, we lose that when the ice gets thick enough. So we really are only seeing the cooling phase and the warming phase. And so the dot plot on the right there shows you that during the cooling phase, we see the travel time increasing, so about 1.6 milliseconds per day. And then in the later phase, we see the warming. So now we see the travel times decreasing. It's getting warmer, the travel times are less. The propagation is faster. And we can do that across all these arrays. So this is these T arrays going to that DVLA there. So there's different ranges in this table right here. So different ranges of propagation. We have a cooling travel time rate at each path and a warming travel time rate. And then we can relate that to an actual cooling in terms of temperature per 30 days. That ends up giving you a nice round number. And what we see very interestingly is very strong warming and cooling signals of the transmissions that are from those southernmost paths, and a very different cooling and warming pattern for the ones that are further to the north. So travel time implies a group speed change. Group speed change implies a temperature or salinity change. Temperature change implies a surface heat flux. This is what everybody wants to get. What's the surface heat flux that gives rise to that warming in that upper layer? And it's about 10 watts per meter squared. So I appreciate your patience in letting me go through some of those details there at the end. They're very exciting research topics that I'm working on. But I hope you have appreciated that national security needs have driven some fundamental discoveries in ocean sciences and will continue to do so. We looked at examples of eddies, internal waves, mixing, solitary waves, climate change, Arctic change, and we look to expand our opportunities for scientists to utilize some of these great national defense systems. So thank you very much. Only 5 minutes over.
Yeah, I don't even know this song.
I think it could be live.
We have questions, please. I will try and get out there and help yell them to him if necessary.
Yeah, I'll try to repeat the question. Any questions about the Arctic? Biology? Waves? We have a hand up. Oh, yeah, very, very much so. Yeah, so, the heat flux into the ocean is changing, and so and it's changing the wind patterns on the surface that's driving the currents and driving the mixing. And so stratification of the ocean, just like I showed you in the Arctic, that warm layer wasn't there 20 years ago. And so climate change is dictating that change in the stratification, which is changing the sound speed profile. And so lots of implications for acoustics, and that's why we're trying to use it as a monitoring device. So it turns out that warm layer, water is coming in from the Pacific. It's a one-way thing, that none of the water from the Arctic goes out through the Bering Strait. It's all incoming. And so in the summer, that water comes in, it sits on that shallow Chukchi shelf, and the sun just warms it up 24 hours a day, right? The midnight sun warms it 24 hours a day, and then it kind of sloughs into the Beaufort Gyre and finds its happy density place. The Beaufort Gyre is full of a lot of fresh water, so you think, why is a warm layer, why is it falling underneath this other layer? Well, that other layer happens to be extremely fresh because there's 6 Mississippi-sized rivers that flow into the Arctic. And so you have that warm layer, and then in the winter, the opposite thing happens. The water sits on the shallow shelf, the heat gets sucked out of it, ice gets formed, it rejects. So when seawater freezes, it pushes all the salt out. So it makes the underlying water saltier, and saltier is denser. And so you got a cold, dense layer, and that's forming that nice Pacific winter water. And then it sits on top of a warm Atlantic layer, which is a whole nother story. Thanks. Yeah.
So you mentioned at the end all the studies that are occurring at the Arctic. Are there any comparable studies happening in Antarctica?
Very good question. Well, one of the reasons the Antarctic, since I do a lot of work with the Navy is not very interested in the Antarctic. But there's quite a bit of activity in Antarctica with the ice shelves there. And that's another region where acoustic measurements could be extremely useful, because you have, a kilometer thick of ice and you have a wide ice shelf, and you can't send vehicles underneath there because you can't navigate. You don't know where they are, where they're making their measurements. And so send sound waves under there and measure the water properties underneath the ice shelves is a very interesting and popular idea. In fact, of course, Munk suggested it 20 years ago, that we should be using that to measure where the grounding line of the glacier is. So you have the ice shelf and then the grounding line from the glacier coming in. Send sound waves up there, reflect off of that grounding line, and see how it's moving. But yeah, Antarctica is very interesting, and it's and the Arctic is turning into an Antarctic region, because Antarctica, the ice is very seasonal. So a lot of ice grows around Antarctica in the winter, and then it shrinks in the summer. Now the northern Arctic is the same way. We're almost seeing like an ice-free Arctic in the summer now. Is there a question?
So you mentioned working with AUVs and acoustic. Have you thought about using them with a LiDAR system to detect icebergs and stuff?
Yeah, I don't know a whole lot about LiDAR in the deep ocean. It may be in a coastal region where you're not worried about seeing things, hundreds of meters down below. But AUVs for sure. I mean, there would be great little mobile receivers that you can move around. And so in the same way you could look at those travel time changes, in the Arctic measured on a fixed set of moorings, you can see as you move your AUV around, you can measure those travel times and get more spatial resolution of where the patterns are warming or cooling. And I think using those in conjunction with a fixed array like that, because then you can navigate where the AUVs are acoustically. You can know where they are within a couple of meters. And so then you have a whole navigated system, and then maybe the AUVs can communicate back, because the ice cover's there. You can't get to the surface to transmit your information back. So maybe you could, the AUVs could get near the mooring and send some of their acoustically modem their data back, and then it can get to the mooring and then out. But yeah, using those in conjunction would be really cool.
Hi, I was just wondering, how did you stay motivated to stay in school for so long?
Well, surfing is always a big motivation. Being a professor allows you a lot of surfing time, especially if you work at UC San Diego or in UC Santa Cruz. But I was just really motivated by learning about the ocean. It was just such an inspiring thing. It was such everything I think about having to do with the ocean is a very happy experience. And so being able to understand how the ocean works and how it affects our climate and our weather, and the organisms that live in the ocean, that's a whole nother lecture. It's just, and acoustics gives you a nice way of looking at kind of all of those things, because you can listen to the organisms in the water. You can reflect sound off of zooplankton and fish schools and see where the fish schools are, and you can use the sound waves to tell you what your CTD instrument should have been telling you. It's just a really neat field where a lot of things come together, not just the physics, but the biology and the chemistry and the geophysics, the geology, and who would have thought, the moon, the oceans are changing the orbit of the moon. So it was just the fascination with that kind of thing kept me going. Thanks.
Some people hold the opinion that physics research accelerates under militaristic motivations. What are your thoughts on that?
What was that about the militaristic?
Physics research accelerates under military motivations.
Oh, right.
So, from a moral perspective, what are your thoughts on that?
Yeah, that's always a difficult thing. And believe me, at UC Santa Cruz, we heard a lot of, I don't know if Mike got much of that, but yeah, the physics students were all kind of gave us a little hard time because many of them were studying, particle physics and were doing, National Science Foundation research, and we were funded by the Navy. But yeah.
Eddie? Oh, here we go.
Oh yeah, the future. I see a lot. I see the Arctic being instrumented with an array like that one I just showed you to be able to have AUVs underwater. It's an acoustic network. It's like an underwater GPS system. And that could also be used, tactically for, monitoring, Russian submarines and other, types of vehicles that were in that area. That, I think, underwater networking is a key part of what we're going to see in the future. Then it's going to involve AUVs too. In terms of research at the lower latitudes, we'll have to see whether having an acoustic network like that gives you more information than if you seeded the ocean with more, drifting buoys or gliders or things like that, or AUVs. It's a much more vast ocean network. It's a much more variable place. The Arctic is pretty good for acoustics because when we're always going to have a winter ice cover. So the wind can't, if we lose the winter ice cover, we're really going to be in danger. So I think the Arctic is a place where I see the most advancement going right now. Yeah.
You mentioned the recent solar eclipse and comparing the recent solar eclipse to earlier solar eclipses. Could you elaborate on that a little bit?
Yeah, so I was just saying how the historical records on ancient eclipses, people were noticing that the totality was moving to the east. So places where you would see, so if the Earth's rotation rate was slowing down, you'd see that progression of the eclipse to the east. And so it appears that has been occurring back centuries. Yeah, I don't have that number right on the top of my head. Yeah, how much and how much further away? I don't know what the recession rate of the moon and the slowing. Yeah, I don't have that right on top of my head. That's a good question.
It better be smaller. We're in trouble.
Yeah, it's very small, but measurable, right?
So, will you be down there in San Diego during summer? Because I will be over there, and
okay. Yeah.
So, after your lecture, I'm also interested in learning more about oceans. And do you know any programs if they have in San Diego University that an international student like me can attend?
Yeah. So you will be in San Diego? Are
Yes.
you in a program? Oh, that's great.
No, not in program, but I will be there in San Diego during my summer break.
Oh, okay.
This summer.
Yeah, I mean, UCSC Scripps has a summer student fellow program, which is excellent. And in fact, they use that to find prospective graduate students. It's a great way to learn about what people are doing at the institution. When you apply to graduate school, a lot of times you'll recognize your name. And Woods Hole also has a very good program, a summer student fellow program, with the same objective of finding talented prospective oceanographers. And having a background in physics is absolutely an A+ thing. Like, I've been on the admissions committees. When we see a physics degree, we're like, yes, this is good. So yeah, that's a great way to get into ocean sciences. It's a little harder to do nowadays what Mike and I did, actually go through a physics department and get a PhD in physics and then kind of go into acoustics. There's just kind of less programs that have people working in kind of those interdisciplinary areas, but there must be some somewhere.
Thank you.
All right, good. Yeah, and if anybody wants to follow up with me, you know, Mike, to share my email, and, you know, I'm, you know, happy to follow up afterward and talk about, you know, graduate school and opportunities and what might be a neat new area of research. If you're working on an undergraduate thesis, maybe some interesting questions you could work on.
If we don't have any further questions, let's thank our speaker one more time. I think we had a QR code slide for the students. There we go. If you were promised extra credit, this is your slide.
Extra credit, yeah.
All right, everybody, thank you very much for coming. We really appreciate it. Have a good night.
All right.